So in the last video we talked about projectiles and how to find things like total flight time, range, and maximum height. In this video we're going to discuss range and how it's affected by the angle of projection and initial velocity, as well as time and how it may or may not be affected by the range. Okay, so let's say, for example, that I have a table. And in one scenario, I kind of push a penny off so that it falls at an angle, some distance away. And then in another scenario, I just drop it from that height. Okay. Which penny hits the ground first? Okay. So remember that horizontal range is independent from vertical range, and the only thing that affects the time in which an object will hit the ground is gravity, right? And gravity is working downwards, and the only thing counteracting gravity is if you have upwards motion. In both cases, we don't have any upwards motion. I just in the first case, I just drop it, and then in the second case, I kind of flick it off, so I have like a horizontal velocity and then a vertical velocity, and then in the other one I just have a vertical velocity. Okay, so if they have the same initial velocity, they're going to hit the ground at the same time, because gravity only works on vertical components, not horizontal components. So flight time is the time it takes for an object to hit the ground is independent from range. So even if an object goes, really far horizontally, it will still hit the ground at the same time it would take another object to just kind of fall that same height straight down. Okay? Obviously this has to be neglecting air resistance. If we had air resistance, it would be a different scenario. Okay, so now switching gears to range, let's say that I kick a ball, and let's say I kick it in an angle of 30 degrees. Okay, so that would be my projection. Let's say I kick it at another angle. Let's say this is 45 degrees. Let's say I kick it at another angle. Let's say it's 60 degrees. Let's say I kick it at an even higher angle, like something like that. So we see that projections are affected by the angle of projection, and then obviously as well as the velocity, initial velocity. If it has a larger horizontal component or a larger initial velocity, it's going to move further in the horizontal direction. So let's say we can we can derive a formula for range. So remember, range is horizontal distance. So let's see, in the last video we had to kind of find total flight time, and then we plug that back in to find the range. Let's see if we can find a formula where we don't have to do that. So in the last video, you might remember that we had to look at both vertical and horizontal motion as two separate entities, and we set up charts that looked at, initial and final velocity, displacement, acceleration, and time with respect to both the vertical and the horizontal. You might also remember that initial velocity with respect to the vertical is given by the velocity at which the projectile is shot from times sine of the projection angle, and that the horizontal velocity is given by the velocity at which the projectile is shot at times cosine of the projection angle. Okay, you would also remember that displacement in terms of vertical displacement is 0. Okay, and that acceleration in terms of the vertical is negative 10. And that's, meters per second squared. And the velocities are in meters per second. Displacement's given in meters. We don't know time. And then in terms of the horizontal, remember that the horizontal velocity remains constant because there's no acceleration with respect to a horizontal motion in this case. So acceleration is 0. And that gives us a velocity. Final velocity is constant, so that's v cosine theta. Meters per second. We don't know horizontal displacement. That's the range. That's what we're really looking for. And we don't know time in either case. Also, you might remember that vertical velocity is just negative v sine theta. So it has the same magnitude, but the opposite direction coming back down. Okay, and we don't know time. Okay, so we're really trying to write a formula for range right here without having to find time and then plug back in every single time we want to find range. So, let's see what we can do. Well, I see that given all the information I have for vertical motion, I can solve for time in general terms. I can solve for t in general terms. So I'm going to do that on the next page. So you might recall this formula. Final velocity. Oops. Equals initial velocity plus acceleration times time. So we know that the final velocity with respect to the vertical is negative v sine theta, initial velocity is v sine theta, and then acceleration is negative 10. So I can plug that all in. And actually, I'm going to go back. And let's just call acceleration due to gravity g. Meters per second. It's going to be negative g because it's in the opposite direction as the initial velocity. It's pushing down while we've defined the upward direction as positive. Just call this g t. Alright, I'm going to bring the negative v sine theta to the other side, and I get negative 2v sine theta equals negative gt. And then solving for t, I get that time equals 2v sine theta over gravity. Okay, so I'm able to solve for time in terms of my initial velocity, gravity, and my projection angle. Okay, now to find the range given this information. Remember, to find the range, all we had to do, because velocity was constant, was delta x, the range, equals the velocity of the horizontal, which was v cosine theta times time. And I can use that formula because velocity is constant. When velocity is constant, remember that velocity equals distance times time. Therefore, distance is velocity times time. You can only do that when velocity is constant. Okay. So plugging in, I get that delta x, put it over here, which is really equal to the range, equals v cosine theta times time, and I'm just going to plug in this guy for time. So I get 2v sine theta over gravity. I can simplify that down and rewrite it as range, which will just symbolize as r, equals 2v squared cosine theta sine theta over gravity. And using a trig identity, we get that, and I'm just going to put the identity on the bottom here in red. Sine of 2 theta equals 2 cosine theta sine theta. So it's just a trig identity that you might know from math at this point. If you don't know that, that's okay. Just kind of follow along as I plug it in. So I get that range equals v squared sine of 2 theta over gravity. So now I have a formula where I can find the range of the projectile given the projection angle theta, gravity, which we know is negative 10 meters per second squared, and v. And it's important to note that this v is the velocity at which I project the object. So that's kind of if you remember when we set up this triangle, I'm really talking about this, the hypotenuse, okay? So let's kind of examine this formula to think about what projection angles give us the largest range. Okay, so we know now that range equals v squared sine of 2 theta over gravity. Okay, so, gravity is constant. It's going to be negative 10 regardless. Velocity, we see clearly that, the larger the velocity is, the further the object will go. That's kind of intuitive. But what about with the projection angle theta? What will give me the largest range? So you might know from math that the sine graph alternates between 1 and negative 1. Okay, so the largest value that sine of 2 theta can take on is 1, which will also correspond to when I have the largest range. So I want to look at, okay, when is sine of 2 theta equal to 1? Well, you might know from math class that sine of theta equals 1 when theta is 90 degrees. So when the angle in here is 90 degrees, sine of theta equals 1. So I'm going to say that 2 theta must equal 90. And solving for the angle, I get theta equals 45. So my largest range is when I project something at an angle of 45 degrees. Now looking back at this diagram, I can see that my largest range, right here, will be at an angle of 45 degrees. Anything smaller than that will give me shorter ranges. Anything larger than that will also give me shorter ranges. There's also a relationship here that when the angles add to 90, they give you the same range. So if I have a projection angle of 30 and a projection angle of 60, that's going to give me the same range given that velocity is the same. Okay. So in closing, we've derived the formula for range in this video, right here, and we found that the largest range is given by a projection angle of 45 degrees. We've also found that time it takes for an object to hit the ground, so flight time, is independent from projection angle. It will take the same amount of time for a ball to hit the ground if I just drop it versus if I kind of roll it off a table, and it has some horizontal motion as well. Okay, so that should kind of wrap up projection. And in the next videos, we'll be talking about Newton's first laws.